Okay, so in the intro module, we went through and we talked about what algebra is and what a function is in algebra. In this course, we're going to be going through three major functions of Algebra 1. The first major function is a linear equation. Now, many have already heard about a linear equation probably even before Algebra 1. But I want to get into a few specifics before we start learning how to, in this first lesson, write linear equations. A linear equation specifically is when the variable is raised to the first power. You have no variables inside a square root. Technically, that little symbol that we call a square root is actually a radical. You have no variables inside an absolute value. Remember, that's the two little bars around the outside of a number or around some kind of variable expression. That means the distance from zero. And you have no variables in the denominator of a fraction. Those types of things cause problems to not graph a line. And so in a linear equation, in order to get a line, you have to have variables that are raised to the first power. So, like I just mentioned, when we talk about linear equations, the reason they're called linear is because the graph makes a straight line. We're going to get into the details of graphing in the next lesson. Also, when we get into the details of graphing, we'll talk about inputs and outputs like we talked about in the first video about functions, where you plug in a number and you get an output. The input-output table for a linear equation always follows a very specific pattern for y values as x increases by 1. That's a fancy way of talking about something that you've probably talked about before, called the slope. The slope of a line is truly what makes something linear. It's the thing that makes something go in a straight line when you have a constant slope, or in the real world we call that a constant rate of change. How quickly the line is moving up or how quickly the line is moving down across the graph. Now we see slope in a lot of other things in life too. We see slope all over the place. When we look at the mountains, we look at the side of a roof. Even something that you might not think about is your salary when you work at a job, and technically if you have hourly wages. If you have minimum wage, it's $7.25 per hour. That's the slope of your paycheck. And I know that sounds kind of weird to think about it that way, but there are a lot of things in life that follow what we call a linear pattern, where they have a slope, a constant rate of change, and sometimes those things also have an amount that it begins at. And we're going to talk about that and how that ties into something that you may be familiar with. Many of you may have seen this representation of a linear equation before. Y equals mx plus b. Now, if you don't remember what this is, it's okay. I'm going to talk about it. But this is called the slope-intercept form of a linear equation. And I'm going to have you some notes here that you can write down in just a minute. But the slope is the m. It's represented by the letter m in mathematics. The b is the y-intercept. These two things are technically what makes something linear on a graph. And we're going to talk about graphs in the next section. But when you have a beginning amount, that's just a number, and then you have a number that is changing the x value, that's multiplying times x, you have a place where your function starts, and you have what it's changing by. And it's a constant rate of change. It's just a number times x. That is truly what makes something linear. And so what we're going to do today is we're going to focus on how do we take that knowledge about having a beginning amount or a y-intercept and a slope, and how do we translate that into actually writing the equations of lines? And so what I have for you here is basically the idea between the three major ways that we'll look at doing that today in this lesson. And we're going to look at one extra little way that you see linear equations in real life also. So, what I want you to do is, if you need to copy any notes during this video, I would like for you to pause the video and do that, because I am going to try to keep this video as short as possible for those that are not taking notes, And for those that may remember some of this stuff, maybe have done a little bit of this before. So if you need to take any notes, you need to write something down, pause the video. There's going to be several times throughout the video that I also tell you to pause the video so you can actually try a problem before I go through it. So basically, we're going to look at three things today with one extra thrown in. The slope-intercept form is the y equals mx plus b, like we just talked about. And when you have the slope and the y-intercept of an equation given to you, all you have to do is plug in the number for m and plug in the number for b, and you have your equation. In a real-life context, we're going to take a look at what that looks like here in just a little bit. It's a very common thing to see in life situations. So first of all, let's look at some basic examples of that. Then we're going to take a look at the point-slope form. This is the one that you use when you have a point and a slope. Notice this point is not the same thing as the y-intercept. This would be like if you have something in real life where you have the rate of change, the slope, and you have just some random information about somewhere later on in time, and you don't have the beginning amount, which is what the y-intercept is. We're going to get into that in a little bit more detail in a little bit. Then you have finding the equation of a line if you have 2 points. And guys, technically, that's what you have to make a line. To make a line, you need 2 points. You can't just have 1 point. That's why the slope is important in these first two examples that we're going to look at, because the slope tells me how to get from one point to another. So if I have the y-intercept or another random point, I can still use the slope to find another point on the graph. So the first example we're going to look at is when we write an equation of a line, and we are given the slope, and we are given the y-intercept. So we're going to write this equation of this line, whose slope m is -2, and whose y-intercept b is 5. Notice, like we talked about, that slope-intercept form, y equals mx plus b. The m and the b are the key things that make this function. And so what we have in the problem is m is given to us, -2. B is given to us, 5. And if that wasn't enough information, it even has the words slope and y-intercept, which is what the m and the b is. That's why this is called slope-intercept form. So my m is -2. My b is 5. And I can take those two numbers, and now I can write my equation of my line. Y equals -2x plus 5. And so this is a linear equation. Like I said, in the next chapter, we're going to talk about, or in the next section, I should say, we're going to talk about how to take this and find the graph of this line so you can actually see that it's truly linear. We're going to talk about several different ways to graph these functions. But notice, again, that it has this slope, this constant number times x, a constant rate of change, which means it's going down 2 every time. And then the starting amount, or the amount that doesn't change, is the plus 5, the constant amount on the end there. So you have this constant rate of change, and then you have this beginning amount, this y-intercept. That is what makes something linear. So take a look at this graph. Okay, we are going to get into a lot more details of graph later on, but you have probably talked about the slope before as this concept of being a rise over a run. Rise over run. And so you have this up to over 1. And so if I'm going up to over 1, that is my slope. That is my m. My b is my y-intercept. My y-intercept is the place where the graph starts. Now, this is a little tricky when it comes to a linear equation because it goes on forever, doesn't it? That's why we're talking about this value here. The y-intercept is the place the graph crosses the y-axis. We're going to talk about that in a little bit more detail as we go through the graphing section on linear equations. So what we're looking at here is we are looking at a point that the graph touches the y-axis. Notice that that is down 4 spaces, so that is -4. So that is y equals 2x minus 4. That is my equation of my line. Now, we're going to get into more detail, like I said, with the graphing of a linear equation in the next section. So hopefully that'll kind of make this a little bit easier to understand. But I just wanted to throw this in here right now to show you a little bit about what a linear equation looks like. So the next thing that we're going to look at is, what does a linear equation look like in a real life context? So sometimes you'll hear a term called a linear model. What we mean by that is when a linear equation models what is happening in real life. It's not a really skinny girl walking down the runway. A linear model is a linear function that represents what's happening in real life. And this is technically one of the biggest reasons we study these functions. We don't go through and figure out linear functions just for fun. That's not our spare time thing. It's because it explains how things work in life. If they have what we call a constant rate of change, that's the slope. And if they have a beginning amount or initial amount, that's the y-intercept. That's the m and the b from my slope-intercept form of an equation. And so what we have is we have things in life that begin at a certain number and move up and down by a constant rate of change. That is what a linear equation is made from. That is the whole y equals mx plus b concept. You have a beginning amount number, and you have something that is multiplying by x every time, and so it is changing at a constant rate, up or down. I also like to tell people this b, the thing you can think about instead of the initial amount, you can think of it as the beginning amount. And then you can also think about, instead of this rate of change for the slope, you can think about that as how something is moving through life. And the reason I do that is that gives you something, to kind of goofy way to remember the m and the b. It's also going to help you a little bit when we go to graph these as well. So let's look at a real life example of that. Linear functions can approximate population change. Now notice what I said there, can approximate population change, because one of our functions we're going to study in this course, called exponential functions, is actually a little better. So we can write a linear equation to approximate the expected population of California in any year between 1990 and 2005. We're going to use the information that is given to us in the problem. It says in 1990, California had a population of about 29.76 million. Notice that's in 1990, the population was this. Why does that make a big deal? Because 1990 was the beginning year. So 29.76 is that beginning amount like we were talking about a little while ago. The beginning amount is the b value, the y-intercept. So now that means we're just looking for the m, the slope. Now that means in real life we're looking for the way that the population is moving. Or, in other words, more proper terms, what is the rate of change in the population? I'll read the next sentence. During the next 15 years, the state's population was expected to increase by an average of about 0.31 million people per year. Notice that it says it's increasing by 0.31 million people per year. Guys, that is what your slope is. That is how the population is changing or moving in an upward direction. So you have your beginning amount and you have what it's moving by. So now that gives me the ability to take that little slope-intercept form like we talked about, y equals mx plus b, and I can write my equation. Y equals 0.31x plus 29.76. I do want you to be aware that you can take that equation and you can also have it p equals for population 0.31 times t for time plus 29.76, and it's still the same concept. Now, I do know that some of you also may be thinking, Mr. Harrison, could I put the 29.76 first and then do the 0.31x? Yes, you can, because in real life, that may be kind of the way you think about it, doing the beginning amount first and then adding the 0.31 million per year, and that's completely fine. I'm just writing it in this format of this linear equation so you can get used to kind of seeing that mx plus b for when we start doing some things again, like I said, with graphing. So now we're asked in part B to use this equation to predict the population of California in 2005. Well, 2005 is 15 years after 1990. So that means 15 years of that increase. 15 years of 0.31 million people per year. So what we do is now we're going to actually use our function. And so this is what is called substituting a number in for x. We are substituting an input in to get an output. That's something we talked about in that function video the other day, and that's something we're going to talk about when we get into the graph specifically of all these functions. So 0.31 million people per year. So I'm going to plug in 15 years of that because 1990 to 2005 is 15 years. Then I take out my handy dandy calculator and I can type this in. Now, if you don't want to use a calculator, that's fine, but 0.31 times 15 might get a little tricky for some of you. So what I'm going to do is I'm going to show you. I'm going to go over here to Desmos. Desmos.com is a great calculator. You already played around with this in your introduction module. Notice if you click on this graphing calculator, it takes you to the main Desmos screen, and you can type in 0.31. You can type in your parentheses 15, just like it is on your paper, and then you can do your plus 29.76. And if you do that, it gives me 34.41. So 34.41 is the answer to how many people in California after 2005. Now be careful, that is millions of people. And that's why it's okay for me to leave that decimal right here of 34.41 million people, because when you are looking at 34.41, 0.41 million is okay. 0.41 of a person, not possible. Can't have half a person, right? Or even 0.4, 41 hundredths of a person. Everybody's a whole person, right? So be careful. Just make sure that your answer makes sense. Now, one thing you do need to be careful of is once I get past 2005, remember 2005 was the ending of this study, so to speak. If I go past 2005, I start to run a little issue with legitimacy of my equation. And so we talk about this in math. That's called extrapolation, when I go outside of my data points, meaning I go outside of the years where this equation is actually pretty good. After 2005, I may need to adjust and have a different equation. And that's the thing about life, is you constantly have to be watching what's going on. All right, here is one for you to try. Don't worry about going through and graphing it yet. We're going to take a look and talk about how the graph of this would tie in, but don't worry about going through and graphing it yet. So what I want you to do is write the equation of the model, and then I want you to use the equation to find the cost of renting a bike for 12 hours. You can pause the video here and try it before I go over it. So we're renting a bike at the Doodle Trail in Pickens, and we're going to rent a bike for $4 plus $1.50 per hour. Notice in a real life context, if you just think about how real life works, what you would do is you would have to pay $4 no matter what, and then $1.50 per hour on top of that. If you're thinking about that just in a real life context, you're thinking, okay, $4 plus $1.50 times, well, I'm going to go for 3 hours, so times 3. Well, in real life, that concept that you just did in your head is the exact same thing as writing the equation y equals mx plus b. was my beginning amount being $4 and my M being $1.50, because my price would go up $1.50 times the number of hours. And so there's my MX plus B. Notice that's the same thing I would do in real life. I would just have a number in for X, but now this equation is useful for me because I can use this equation to find the value after 12 hours by plugging in 12 for the number of hours, doing 1.50 times 12 plus 4. So I take out my handy dandy calculator again, and I'm going to go and do 1.50 times X. And so I'm going to be plugging in 12 and then plus 4. Oh, guys, and I just realized that you can't see this because I was not on the sharing portion there. Let me go back to here. There we go. You should be able to see it now. 1.5 times 12 plus 4 equals 22. And actually, I think you might can see that. I hope so anyways. Sorry, guys. I know. I should know how to do my technology, right? So $22 is what that would cost me. Now, that's great and fun if I know exactly how many hours I'm going to be biking. But there are other times when in real life you have this concept, but instead of knowing how many hours you're going to be biking, you know that in your wallet you only have a certain amount of money. Let's say you know that you only have $15 in your wallet. If that's the case, I can't plug in 12. I know that 22 is going to be too big, but I can plug in 15 for the Y value instead of the X value. And so this leads me to an equation that only has an X in it instead of a Y equals like this one. Because $15 is the total cost. X is the number of hours. Then I could take this, and I'm going to do a little bit of review of solving here because you've probably remembered solving equations before. We're going to do another specific video on solving equations a little bit later. But if I subtract 4, you're going to get 11, and it equals 1.50x. We divide by 1.50 because it's the opposite of multiplication. And we take out our handy dandy calculator. Oh, sorry about that, guys. And we do 11 divided by 1.5, which gives me 7.3 repeated. If you need to get your answer as a fraction, which you shouldn't in this one, we're talking about hours. But if you need to, there's this little button that looks like a little fraction. You can change that 7.33 back to a fraction. And the good thing is it'll always reduce it for you too if you need it to. But X would be approximately 7.33. Now, what does that mean? Well, that means if I am trying to ride this bike, I only got $15, I can only ride for 7 hours and a little bit over that if the bike company that I'm renting from allows me to. If they don't allow me to do a partial number of hours, then what I'm going to have to do is just stop at 7. Also, then you can make decisions in real life of, hey, if I have $40, am I still going to have time to ride the bike 12 hours? And then can I get something to eat for the rest of that? That's where understanding how the mathematics works. I'm not saying you're going to have to go and pick up a piece of paper and a calculator and actually write down your equation every time you go rent a bike. That's not what I mean. What I mean is you need to understand how this mathematics stuff works here so you can actually make important decisions about your money. All right, so now what we're going to do is we're going to move into the next type of problem. The next type of problem is when you have what we call point slope form. Now I'm going to rewrite the point slope form. It was on that first page if you took some notes on that page. But point slope form is y minus y1 equals m times x minus x1. In other words, you have the slope right here, and then you have the x1 and the y1 are numbers from a point. When we say numbers from a point, what we mean is numbers that are found in a point on the line that is not the y-intercept. Or in other words, in a real life context, it would not be the beginning amount. It's some other amount that's on the line. It's some other amount in the real life situation, but it's not the beginning amount. So what we do with this is we use this point slope form if we have a point and a slope somewhere on the line. So what we do is we take this 6, -3, and this slope of -2. We know that slope is -2. We do not know what the y-intercept is. We don't know what b is. But we do know that 6 and -3 are an x value and a y value from a point. The x sub 1 and y sub 1 don't really do anything mathematically. All they do is tell me that it's a point somewhere on the line. It's just another point, not the y-intercept. So what we can do is we take this little formula and we just use the formula, kind of like we did the other one. We plug in what we know. So we plug in -3 for y1. We plug in -2 for m. We plug in 6 for x1. And now this is called point slope form. Now if you are in South Carolina, there's an end of course test for Algebra 1 where they'll expect you to probably know the point slope form. Algebra 2 teachers will probably expect you to know the point slope form. But technically, you can also use the slope-intercept form to find the b value too. Anytime you're missing something in mathematics, plug in what you know to find the thing that you don't know. Now in this case, I'm looking for the equation of the line. So what we're going to use is some old stuff, some pre-algebra, or the early parts of Algebra 1. We review this. -2 times x, because this is the distributive property multiplying, -2x. -2 times -6 is +12. Over here, when you have minus a negative, remember that's the same thing as y plus 3, because there's a little rule that you can use called leave, change, change, or the fact that subtracting a negative is the same thing as adding a positive. So then what you can do is you can subtract this 3, and it gives me y equals -2x plus 9. And so that is my equation of my line. So notice, just like we finished on the other problems when we were trying to find the equation that works, we had the m and we had the b given to us. We just plugged them in. But now we have to find the b. So we got to do a little extra work here to find what that beginning amount, if you're thinking of real life, or that b value, if you're thinking of just y equals mx plus b, or the y-intercept if you're thinking about the graph. Again, I know we're going to talk about the graph in a little bit more detail later. So I have one for you to try now. This one does require you to know something about parallel lines that you learned in middle school. So if you want to pause and try it here, you can do that. If you want to watch my explanation, then go back and try it again later and see if you got it. Or try some of the practice problems in the homework. That's fine too. So we're going to write an equation of a line that is parallel to y equals 2/3 x minus 2. Now the basic idea is that parallel lines don't touch each other, right? What that would mean in reference to linear equations is that the slope, the rise over run, would have to be the same. There is no way that you could have different slopes and the lines not touch each other. So at some point, if one of these lines is just a little bit off, it's going to touch the other line. But if they are the same slope, then they're parallel. So what does that mean? Well, if I want to go parallel to y equals 2/3 x minus 2, notice the whole mx plus b thing again. That is my m for the line that I'm looking at, but that should also be the m for the line that I'm trying to find, because that is the original line, I'm looking for the line that's parallel, which means it has to have the same slope. So now I have a point that it passes through and a slope. In other words, I don't have the b, I have the point, the x1 and y1. Now, if you couldn't get to this point earlier, now maybe you can pause the video here and try it. So I'm going to use the point slope form, y minus, and I'm going to plug in the y value. M, which is my slope, times x minus the x value of -2. That makes this be 2/3 times x plus 2. So what do? I'm going to distribute this. 2/3 times x, 2/3 times 2, that is 4/3. Yes, guys, I did that in my head. You can use a calculator. Then I take this and I add 1, and I'll get my equation of my line. Y equals 2/3 x, 4/3 plus 1. Let me show you what that looks like on the calculator so you can actually see that happen on the calculator here. So if I do 4/3 plus 1, I got 4 divided by 3. Press the arrow over, hit plus 1. It tells me a decimal. Decimal is kind of ugly. Maybe a good idea to keep an exact number. So I'm going to hit this fraction button. That gives me 7/3. So 7/3, or 7/3. Yes, as a decimal, that is 2.33. And the decimal will become important when we actually start talking about the graphs of these and trying to graph this. That decimal may help you a little more for this number, particularly. Not for the slope, though. Remember, the slope is that whole rate of change, the rise over run, what the line is doing across the graph. All right, here's an example of this in a word problem. So take a minute, pause the video, and read the word problem. Now that you've read the word problem, you can see that between 1985 and 1995, the number of vacation trips in the United States taken by United States residents increased by about 26 million per year. Notice this, increased by 26 million per year. Think back to that other problem we did with the word problem a little bit ago. We talked about in real life, the m, the slope, is the rate that it's changing. This one is increasing 26 million trips per year. That's the rate that it's changing. Well, what about the beginning amount? Well, just like we had earlier, we were looking for the beginning amount to be able to write an equation of a line. We're looking here, and it says in 1993, United States residents went on 740 million vacation trips. In 1993, they went on this many million vacation trips, right? But that's not the beginning amount. Yeah, it is, Mr. Harrison. No, it's not. Look closely. If you read the sentence, between 1985 and 1995, this is when the beginning happened. This, 1993, is not the beginning amount. Neither is the 740, which is actually the true y value there. What that is 1993 is 8 years later when there's 740 million. The beginning was 1985. 1993 was 8 years later. Well, I don't get it, Mr. Harrison. Why'd you put 8 instead of 1993? Because the beginning was 1985. 1993 was 8 years later. You don't want to start with 0 being the year actual 0. So if you accidentally put 1993 right here, you would be telling me that there's a United States in the year 0. Let's hope our history is a little better than that. Let's hope our math is better than history, if that is how bad our history is. But there was no United States in the year 0, right? Yes, I know the actual continent was here, right? And the actual land mass, but not the actual country. So 8 years is what we're going to use for our x value. Now, some of you may be thinking, okay, Mr. Harrison, how do you know that the x's are the years and the y's are the trips? Well, right here we have 26 million trips per year. That lets me know that it's the change in y over the change in x, like we've seen with our slope in the past. Slope is always going to be change in the y over change in x, or like you guys say, rise over run, right? Now what I can do is I can use my point slope form again. Y minus 740, 26 times x minus 8. 26 times x is 26x. 26 times negative 8 is negative 208. Then you have minus 740. So you add 740 to this side, add 740 to this side, and you get y equals 26x plus 532. Now, some of you may be out there thinking, 26 million a year, 8 years, 26 million a year, 8 years, 26 times 8, that's 208. Then I can just subtract that from 740, and that'll give me the beginning amount. I can get the B, 532, without having to do that stupid equation. Well, number one, if you just listen to what you just said about thinking, you just did exactly what I did. I did 26 times negative 8, because it's going back 8 years, and I did plus 740, because that positive 740 minus the going back 8 years is 532. I just have a nice little way to follow every time, nice little steps. You were just using your head, using your brain, and it's smart. It's not dumb. It's just I want you to make sure that you understand. If you use these little formulas, it'll help you do it a lot quicker and a lot more efficiently every time. Now we're going to do something I talked about on the other problem. We're going to kind of extrapolate here a little bit. We're going to estimate the number of vacation trips in the year 2005. 2005 is 20 years later, but that's kind of outside of our original range of numbers to 1995. So 2005, 20 years later, if I plug in 20 and I do 26 times 20 years plus the 532. To save a little bit of time here, I'm going to go ahead and show you what that is. That's 1,052 million trips. Now, that might sound a little crazy, but million trips there, 1,052 is the same thing as a billion, 52 million. It sounds like a lot, but remember, vacation trips can be something, even short trips. In the United States, you could have 300 million people going somewhere a couple times a year. That's not the problem. The problem is because we extrapolated what we didn't take into consideration, especially because this is talking about 2005. In 2001, there was a pretty big event that changed vacation trips and traveling for quite a while. Now, it didn't totally get rid of it, but 9/11 had a lot of people scared to fly on a plane and scared to go on traveling places. So be aware that that's the reason we have to be careful with extrapolation. This equation is making a prediction about 2005, but it may not be the best prediction because that's outside of our range. All right. The last thing that we're going to look at here is we're going to look at what happens if we are writing a linear equation when we are given 2 points on the line. This is when we do not have the slope handed to us. We do not have the y-intercept, the b-value, handed to us. We only have 2 points that make a line if you connect the dots. Again, now we're going to talk about the significance of points on a line when we start graphing them in the next lesson. But what we're looking at now is just trying to find the equation of the line. And I made a mistake, guys. I just said this was going to be the last thing. I got one more sneaky little thing to throw in at you. Another quick little thing about graphing lines. Or, about writing equations. So, we're going to write the equation of this line that passes through these 2 points. We still need the same 2 things we were looking for a minute ago, the m and the b. We don't have the b because it's not given to us. There's no y-intercept given to us. But we do have 2 points that we can do our little slope formula. Now, for those of you that don't remember the slope formula, I'm going to write it down, y2 minus y1 over x2 minus x1, the change in y over the change in x, or rise over run. So now we can take it and we can do -4 minus 6 over 3 minus 1. y2 minus y1, x2 minus x1. -4 minus 6 is -10. 3 minus 1 is 2. -10 divided by 2 is -5. Now you have your m. You have your slope. Now I can do the same thing we just finished on the last few problems. I have a point and I have a slope. I can use my point slope form. Y minus the y value of 6, -5 for my m times x minus the x value of 1. And I distribute this to both of these, the distributive property, -5 times x. -5 times -1 is +5. And then I take this -6 and I'm going to add 6 to get it to move to the other side. Cancel out here. -5x plus 11. That's my equation of my line. And guess what? If I'd used the 0.3 -4, it still would have worked, because my b value would still be 11, no matter what. So when you have 2 points on a line, you find the slope first, and then you do the same thing that we did on the others. So the key thing with all linear equations is getting that slope and that y-intercept. There is going to be kind of a little special type that I'm going to show you here in just a second. Before I do that, I do want to point out that if you're dealing with a word problem, what you'll notice a lot of times with a word problem with these is you'll see things like this, like person 1 has this femur length and this height. This femur length and this height. That is 2 points. And we're describing, in this case, I know we didn't go through this whole example, but a group of people, we're going to use these 2 complete adult skeletons to find out a linear equation that describes what the height would be depending upon what the femur is for your x value. So these 2 people would give you the equation, and then you could use that equation, in this case, to estimate how tall this guy is, where we only found the femur. And that's what people like archaeologists do. And they study things and they use mathematics to help them make predictions about stuff. But, sometimes they have to readjust their formulas and stuff. So make sure you pay attention to that when you're studying science. Make sure you go through and you realize that, hey, they're constantly correcting things. So make sure you're continuing to go back and read and learn, especially when they start talking about important things that deal with our life. Okay? So let me show you one more example of that with 2 points here. Notice it says in 1970, there were 160 African American women in elected public office. By 1993, the number had increased to 2,032. Notice there's a time and an amount. A time and an amount. That would give me the ability to set up 2 points. Now I'm going to show you a little tricky spot on this one. The amounts are the number of African American women in office. The times, it's probably going to be better to take 1970 and 1993 instead of using the actual years. Remember we talked about on the other problem, that would mean the year 0 is the beginning. Actually make 1970 year 0, and 1993 would be 23 years later. So this would actually be the beginning year for us instead of 0. That way, we can actually make that be 0, and our equation doesn't look ridiculously ugly because we're thinking about the beginning of the year 0, actually, when there was no United States. So that is an important thing to notice. All right, so the last little bonus way that I'm going to show you about writing equations of lines is going to be something that's a pretty common thing, especially if you're kind of a high school student. You'll see this from time to time with little things like a fundraiser. And what I mean by that is, typically in things that are like fundraisers, or if you're selling something, you have a couple of items that you're selling, or a couple of items that you're trying to raise money with. One thing in particular that I usually like to use with my students is I talk about a t-shirt sale and a hat sale. Let's say we got Pickens High School Blue Flame t-shirts and hats. Let's say the t-shirts are $20 and the hats are $25, because typically hats are probably a little bit more expensive to make. If I want to figure out how many of each one of these I need to sell, notice what I said. If I want to figure out how many, I don't know how many yet, but I want the total amount of money that I get to be $2,225. I need to be able to figure out how many do I multiply times 20, how many do I multiply times 25, and add that together to get the total. Notice what that means. That would give me 20 times, let's use X, because I don't know what it is. I don't know how many I'm going to sell. Plus 25 times Y, because that's going to be a different number than the number of t-shirts, and I don't know how many I'm going to sell, equals 2,225. That is also a linear equation. Notice if I wanted to get this to look like the y equals mx plus b stuff that we've just been talking about, I would have to take this guy right here and I would have to move this x over here, and then I'd have to get rid of this 25 by dividing. We're going to talk about that in a little bit more detail when we go into the graphing side. But that is still a linear equation because notice the variables are raised to the first power. So don't get bogged down and forget that linear equations don't have to be slope-intercept form. It's just the most common, and it's one of the easiest ways to work with it. But this one right here is also a fairly common example, especially in some of your basic kind of fundraisers in high school, where you have a company that's selling two things. Mr. Harrison actually owns a gym that has $90 memberships and $75 memberships per month. And if I want it to be a certain amount of money every month, I've got a linear equation that gives me a way to figure out what X and Y could be. Now, I'll give you a little hint about what we're going to talk about with graphing. It's not going to be just one answer, 1 point, because graphing is how we actually find the answers that work for this equation. So that's a little hint of what's coming up with graphing. And that's what a lot of math teachers actually do a bad job of explaining. The whole reason for graphing is not just for fun graphing. That's why I decided to do graphing after we wrote the equations, because the whole reason for graphing is to be able to take these equations that we don't really know anything about, like how many t-shirts, how many hats am I going to sell? That's where a graph is actually going to give me the answers. So we're going to take a look at that. Make sure you go through and practice your problems about writing linear equations. Your linear equations picture project also involves you writing equations of those lines. So that'll be coming up. Make sure you read the assignments page on that.